I can't resist getting sidetracked by sine and cos a little bit before talking about the derivative. Sine and cos are easily the most important equations that I can think of when you go to talk about really large concepts in engineering and science. Because sine and cos describe waves, which is everything. I don't know how far they've got with chemistry on the whole wave thing. You and Mrs. Todd don't really sit around and talk about it at the dinner table about what you're learning in chemistry. But it sort of started off with electrons, that maybe electrons were these little planets that rotated around the center. And the history of that is kind of weird because they didn't know what the heck was going on with the atoms. So they modeled it off something they could already see. It was like, oh, maybe it's sort of like the planets. And it does have some analogies to planets orbiting around the center. But really, when you really start exploring it, it's not really much like that. So you guys are probably learning about different orbitals and how these things behave here. And even it's just a way to explain it. It's a way to do the math. What really seems to be going on is there's this electron wave around the outside. And these electrons could be just about anywhere. And all we can calculate is the probability that they'd be in a certain spot. So there's these giant wave functions in 3D, mind you, that describe where the electron might be. The question of where is the electron, that's a tough one, yeah? Because that might not be quite what we think it is, that the electron is anywhere. It's where, as soon as you go to grab it, or as soon as you go to measure it, that it takes on some kind of meaning about what an electron is. If that boggles your mind, it's boggling all the physicists' minds. It has been for the whole last century. Like, what is an electron really? Not what we model it as, so that we can do calculations and make chemicals. What's really going on in there? Anyway, the basis of all that stuff, you need sine and cosine. Okay, next. You learn a lot about polynomials. 3x squared, 4x cubed, all those kind of things. And for a while, it's like, but it doesn't seem like any of the actual equations in science and engineering are actually polynomials. Why are we spending so much on polynomials? And why so much time on sine and cos? Well, the thing is, polynomials and sine and cos can be used to model all functions if we need to. There's ways to do it. It's sort of a year 2 university thing, and you find out, oh, that's why the weapons of polynomials and sine and cos are so important, because any function you want, you can use these if you really need to. It seems unbelievable that that could possibly happen, but it's really rigorous and really awesome. Anyways, sine and cos, vitally important. For our purposes now, though, sine and cos, as they always were, between -1 and 1, and a lot of radian stuff, yeah? The derivatives. Here's the great news, though, after all that's meant to blow your mind, but this shouldn't blow your mind. Derivative of sine is cos. How nice is that? And by the end of this lesson, you get a little taste of why that might be true. It gets better. Derivative of cos, negative sine. Take a while to really get why that negative pops out of there. You know, but during this lesson, you might see exactly why. Or in Leibniz notation, which I continue to try to introduce here, d by dx of sine x is cosec, d by dx of cosec is negative sine x. Now, this d by dx means, yes, take the derivative. The d stands for derivative, simply enough. And by dx means the independent variable you're going to run into. Well, let me go one step farther. The independent variable you should be thinking about when you take this derivative is x. You see t's, you see y's, you see other things. Don't worry about that. Go after x. That's a little bit better explanation of what Leibniz is all about. On a separate page, do these proofs. Oh, I don't need a separate page. I got Active Inspire. Here I go. The derivative of 17 sine x. Let's just talk about something different for just one moment. The derivative of x is 1. Oops. The derivative of 17x is 17. See, when there's a coefficient out there, we don't really need to incorporate the derivative into this whole thing. Yeah? The derivative of x is 1. So the derivative of 17x is go, okay, bring down the 1, multiply it by the 17, and I got an x to the 0, so I'm right down to 17. You see, all these rules work together. After seeing all the lessons I've done so far, some people will automatically do this. They'll go, oh, it's a product. Product rule. Because it is a product. So they do product rule on this thing. They go, derivative of the first, derivative of 17 is 0 times x, plus derivative of the second, which is 1, times 17. And lo and behold, yes, you can do product rule. That's still a thing. But let me just re-say it. When there's a coefficient, a whole number coefficient, a constant coefficient out there, we can just treat it like a coefficient and just find the derivative of the other piece and multiply it by 17. We did it here. We said, okay, y prime is 1. When y was 17x, we went, okay, yeah, 17. I got it. 17 times, yeah? But meanwhile, the derivative of x is 1, so it's 17 times 1. So the derivative is 17. All of that so that this doesn't seem weird at all when I go, if the derivative of sine is cos, the derivative of 17 sine is 17 cos. After my semi-dramatic introduction to this whole lesson, that might seem like pretty straightforward stuff, and it is. Derivatives of sine and cos are pretty straightforward stuff. Any questions about that derivative? X squared minus cos x, y prime. Derivative of x squared, 2x. Derivative of negative cos, okay, so that negative, again, is just like a coefficient, like a whole number coefficient. It's a negative 1. Yes, I know it's there, but I don't really have to worry about it. I go, yes, negative, and then I just look at cos and go, what's the derivative of cos? The derivative of cos is negative sine. And so I got a negative that was already there. Then I got a negative that comes out of the derivative of cos, because the derivative of cos is a weird negative sign. And so the derivative here is just y prime equals 2x plus sine x. You might get to the point where you're good enough that in the middle of all that you could do that in one line. But for now, I don't think so. Just work your way through them, because I think you're going to find this, the trig questions, compared to the product rule and quotient rule stuff you've been doing, pretty nice. As long as you know derivative of sine is cos, derivative of cos is negative sine. Questions there? I mean, you can go on and do questions where they say, oh, what's the derivative when x equals pi over 4? So you plug in pi over 4. Well, when is the derivative of 0? So you put a 0 over there. All those questions still stay the same. We're just doing the derivative part of it. Oh, here's a little refresher. Okay, this 7 over x cubed. Again, I really want to get on about this 7, because the 7 was no big deal 2 lessons ago. And then I taught quotient rule, and now you see these 7s in there, and you go, do I have to do it as quotient rule? And the answer is no, you don't have to do them as quotient rule, because this is just a whole number multiplier of the whole thing. So if it's just a constant multiplier of the whole thing, you can just treat it like a coefficient and just leave it out front sort of things and go, okay, there's a 7 out front of this thing. I'm multiplying my answer by 7, but I just got to find the derivative of the other parts. If you do the quotient rule, it will work out. So it's not a mistake to do the quotient rule. It's just extra work you don't need. This thing is not ready to take the derivative. And if your instinct was to go after that as a quotient rule, again, it will work. And I'll do it off to the side over here. Here, if I treat that first thing like a quotient rule, watch what happens here. Y prime equals derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. And I get y prime equals negative 21x squared over x to the power 6. And I get y prime equals negative 21 over x to the power 4. Okay, so there's the derivative of it using the quotient rule. So if you look at that one, it's got to be quotient rule. That's a quotient. I'm like, yes, you can do it that way. But if you just go here, y prime equals negative 21, x to the negative 4, you see how much nicer that is. So when it's just, again, if it's just a constant coefficient, just leave it out front, take the derivative of the other part of it, multiply at the end. And a quotient rule will get you there, but boy, what a long way to go. Again, constant multiplier here. Constant multiplier here of negative 4. So, yes, I know about the negative 4, but because it's a constant multiplier, I just leave it as negative 4, and I go after the derivative of cos, which is negative sine. We did an activity with the calculator where we sort of saw that the derivative of sine was what was cos. There's some, and again, this lesson has a little bit in it to show why it could or why it should be cos. So I'm going to just tidy this up a little bit. Then you can do whatever. Sub in the number they give you. If they want you to do that, find the slope at x equals 7, you know, or whatever. You're ready to rock and roll there. Questions about that one? We're on slide 3 of 6, by the way. Although slide 6 has got a couple-minute demonstration I got to do in there. More time? What rule has jumped in here now? For y equals x cubed times sine of x. Two things multiplied together. Going product rule. So underline the first one, and you're going derivative of the first times the second. Plus derivative of the second times the first. If that's a problem for you, that I did it that fast, it's not panic time. It is time to get to work on the product rule homework, though. You've got to be good at those to be able to handle these. And so just to tidy things up a little bit, 3x squared sine x. And we really, really want to write polynomials in front of sine and cosine. Sine and cosine, we don't want them. It gets confusing if you leave the x cubed out there. Because is this cos x times x cubed? Or is this cos of x times x cubed? You know what I mean? Like, so it's a little confusing to put it back there. So we try to put those out front. And as you're doing them, you might even, as I remember when I did derivative of the second, and when I went to write times the first, you probably want to just write it over there right to begin with. You're not going to write these things at the end. I know the rule says do it this way, but you put those terms in the place that's most convenient for it. That's really good. And especially during this COVID thing, I'll take that. But we can do a little better. This thing has a common factor in it. So I factored the x squared out of that pile. And just trying to build that in as a habit. We really want to factor these things when we get a chance, depending on what we're going to do next with it. If you're just subbing in a number, well, factoring isn't the most important thing. But if you're trying to find the derivative of a certain value, like if you said, okay, when does the derivative equal 0 here, factored form is going to be the way you want this thing. Questions there? More time? More time? Who needs more time? Ooh, okay. Hey, put down my controller. I'm getting out for this one. What kind of rule am I going to need on this thing? Quotient rule. So I'm going to teach it slowly, just in case you're not quite caught up on quotient. You're like, I'm not clear on quotient. Let me just go through quotient rule again. Derivative of the top. Times the bottom. Minus, with quotient rule, derivative of the bottom. Times the top. All over the bottom squared. Derivative of the top, negative sign, times the bottom, yes, 1 minus sin x, minus derivative of the bottom. Derivative of the bottom is negative cos x, times top, which is cos x. What is it about this situation that tells me I got to multiply out the brackets? Subtraction. This is good, nicely factored, but the top needs some work, so. that is not all. Not too many identities yet. I'm not going to beat you to death with too many identities, but boy, this one I hope is starting to get familiar. Sine squared plus cos squared just randomly popped out of this, which is 1. I could write plus 1. Sort of want to get you in the habit of going, when you go to write plus 1, go, is there a better place? Negative sine x plus 1? Maybe the 1's a little bit better out there. But that is not all. And this happens all the time with derivatives. You think it's just some random setup? It's not. Like all the time we're doing derivatives of stuff involving sine and cos, using identities and using factoring and canceling and these kind of things. Good things happen. I got 1 minus sine x over 1 minus sine x squared. One of them goes. So I cancel 1 minus sine x on the top. And I cancel the square on the bottom. And I'm left with 1 over 1 minus sine x. And it happened again where the derivative, lots of times, is much simpler than the original function. Was that the last of the regular derivatives? Any questions about those? More time? Back to the PowerPoint. I did those. The caution, the following may lead to a very deep discussion. No, I'm not going to make it too deep for now. I'm just going to tell you about this situation and what's come up here. Up to this point, we've been using only radian measure. If y equals sine x, where x is measured in degrees, is the derivative still cos x? I'll say it's close. It just needs to be modified by a little factor. All this stuff is set up for radians. From here on in, if it doesn't say an angle, you should assume radians. If you're on the science engineering path, it's radians the rest of the way, baby. We almost never use degrees unless we're talking to non-math people. And then when we're talking to non-math people, we're like, okay, well, let me put it in degrees for you so you have a chance of understanding, okay? Degrees is for building sheds. You know, that's what we use degrees for. Radians is for anything advanced at all, okay? So, we need to be in radians when we're taking derivatives. I'm lying a little bit. There is ways to manipulate this to work with degrees, but it's got all sorts of extra fixed factors and stuff like that. It's not a fun way to handle things. Simple harmonic motion, have to address this, have to talk about this because it comes up in every branch of science. There's lots of things that do this simple harmonic motion, from sound waves to pendulums to things bouncing on a springs. And why this is important for you potential chemistry people is the models of bonds and so on talk a lot about things that are sort of on a spring, you know, and certainly the laws of thermodynamics, when you talk about temperature and so on, we talk about how bouncy things are and how they're bouncing off each other, and then these bounciness equations start to come into things. So example, well, I think I put this example on a separate thing. I'm going to focus a lot on the pendulum today, and we call it a simple pendulum because there's a lot that can be talked about. You can use everything you talked about in a pendulum to talk about a tuning fork, and you can talk about sound, just from the examples you get from a pendulum. And certainly things that are bouncing on springs. It all comes from the pendulum. The pendulum will get you there. So here's the example. And most of it is really easy. And at the end, I got a little explanation. It says a weight hanging from a spring is stretched 5 units beyond its stretching position. So you've got a weight on a spring like this, and somebody grabs it after it's sitting there and pulls it down. And then lets it go, and the thing goes boing, 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 up and down. Now, just like we had to ignore air resistance, we're going to have to ignore friction, because something that bounces up and down like this will eventually slow down and settle in. Yes, when it's bouncing up and down like that, normally. We're going to ignore that for now. We can deal with it. We can, but we just don't have the mathematics yet to deal with it. So for now, imagine a spring that I let go, and it goes boing, 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 forever, essentially. Okay? Its position is later at time t is given by s equals 5 cos t. Does that make sense? It goes out to positive 5, then back to 0, then to -5, then to 0, back to +5. Do you see how cos is the perfect function to model this? Because cos does 5, -5, 5, -5, and just goes back and forth. By the way, it's not hard to model something that slows down. 5, -5, 4.5, -4.5, and is slowly slowing down. That's not hard to do. We're just not happening to do it today, okay? So here's s equals 5 cos t. And all this question asks for is the velocity. So the velocity will be s prime, which will be -5 sine t. Pretty easy stuff, actually, taking derivatives of sine and cos. The interpretation is going to be the tough part. And then finally, acceleration, which would be v prime, which is s double prime. It just means I take the derivative again. I get -5 cos t. Isn't that simple? It stays nice and simple. Displacement, velocity, acceleration all stay pretty simple for sound waves. So that would be easy. Up till there, we're like, yeah, what is the velocity and acceleration? Pretty straightforward, and you could sub into it and all that kind of stuff. Then it says, describe its motion. Yeah? Things sort of go wild. So I really want to show a really cool video I found in like 4 seconds here. I mean, it took me 4 seconds to find it. I'm going to run the video. I might rewind it a few times. And here's a simple pendulum going back and forth, and might tie together a lot of the stuff I've talked about today. This pendulum, if we want to just talk about its displacement, when it's over here, we're going to say 0 is the center, right? So when it's over, ooh, it's already got to velocity. I'll rewind it. I'll just focus on displacement for now. When it's over here, just like when I had the 0 here, when it's over here, it's got displacement negative. Displacement 0, positive. Do you see how sine and cosine come out of this now? 0, negative whatever, -1. 0, positive. 0, negative. 0, positive. 0, negative. 0. So the pendulum, its displacement perfectly models a sine function. Back and forth and back and forth and back and forth. Good? Now let's go after velocity. This is where this really gets, it's one of those situations that gets so complicated, and then all of a sudden it's so simple. Let's talk about its velocity if I run this thing. Velocity. And I'm going to stick right with it. Heading this way, positive velocity. Stops. So 0. Now, negative velocity. Now, 0. Now, positive velocity. And see, look at it. They put a little arrow on there. So see, positive velocity, 0 velocity. Now, negative velocity going that way. Now, 0 velocity. Now, positive velocity. And it perfectly models, I'm going to pause it there, perfectly models a sine or a cosine function, just going positive, 0, negative, positive, and just it does exactly that. It gets better. The acceleration does the exact same thing. It's going to switch over here in just a second. It's showing velocity right now. Watch, it'll show acceleration here in a second. Here's acceleration. When it's on that side, it accelerates towards the center. When it's over here, now it's accelerating that way. When it goes onto that side, now it's accelerating this way. So, positive acceleration, 0 acceleration, negative acceleration, back to 0. See, it's another perfect sine or cosine curve. You think this simple pendulum, like, okay, good. Like, who cares about a simple pendulum? Unless I'm pushing my kid on a swing, what do I really care about all this stuff? And I got to be honest, when I push my kid in the swing, a lot of the stuff's going through my head. The kids tell me a story, meanwhile I'm going, wow, the acceleration, the velocities. So, I'm thinking about all these things. But this simple model expands nicely into sound waves, electrons, water waves, anything that has to do with periodic motion. This simple model maps into that. Notice the story isn't over for you physics people. We've got weight and we've got tension in there now. We got kinetic energy, we got potential energy, all this stuff doing the exact same stuff. So lots and lots going on here. Now, let me just stop the video at exactly the right moment for us. In this course, for you non-physics people are like, oh no, here we go with the physics. No. 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 There. We stop at acceleration for now. For you physics people, then you take it the step farther and deal with these other things. All that angles that we're going to have to deal with, sine and cosine. See, there's a little angle in there, so sine and cosine pop out of this nicely. That's my description of the motion. The motion starts with negative displacement, then goes 0, positive, and that's why you get this sine curve. Velocity starts with positive velocity, then 0, then negative. That's where you get the sine and cosine out of it. Why the positive and negatives? Because the positive and negatives all don't match up here. When this thing has negative displacement, it has positive velocity for a while. So the sine and cos, the positives and negatives, and the equations all match up nicely so that you're getting the right things at the right times. Yes? Oh, this is so, for you physics people, this is such a good video showing off the balance between kinetic energy, total energy, and gravitational potential energy. How far have you got with all this stuff? It's the perfect, this is what people need to see about what's going on with those relationships between those energies. Anyways, where was I? Oh, I was done. Okay. Much more complicated than what we teach in this course. Much simpler for actually doing the math. You saw the math here. I think the derivatives were the easiest ones we've done in a few lessons. Just like boom, 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 boom. Pretty straightforward stuff.